Okay, in this video we want to practice some more solving linear systems with substitution, and there's a couple of, you might be wondering why substitution, blah blah blah, like why would you bother doing it? Well, if we compare it to actually like the graphing method that you did, sometimes graphing can actually suck. Okay, it can be actually hard to do if you don't have graph paper and straight lines, and that kind of stuff. Graphing can actually be really hard to do. Especially if the answers are not exact coordinates. If they aren't exact coordinates, it can be really hard to actually know what the exact answer is. Sometimes you need to know exact answers. So graphing can suck, can be time consuming sometimes, and getting straight lines and the right points and having graph paper and all that kind of stuff. And if you don't have the nice exact intercepts and coordinates, it can be really difficult. So the substitution thing that we're doing is often best for more exact answers and compared to graphing and stuff like that. Especially if the answers are like fractions or especially decimals, it's way better for more exact answers and things like that. And also it's really good for more complicated expressions. Okay, you guys are just starting with linear stuff. Expressions get way more complicated. There's formulas out there. There's a bunch of crazy stuff out there, and you can have some real issues graphing stuff like that. Really hard. So substitution is really good for exact like decimal type answers. It's way better for like complicated expressions and stuff that there's just advantages. And there's a third method that we'll look at as well, but substitution is probably one of the more beneficial, useful overall type strategies to use. Okay, so let's do some more practice of that a little bit today and see what we can do with that. Okay, so here we're going to give some expressions here like last time. I've got the general steps here from last time as well. So let's try this. We've got negative 6x plus 7y is equal to minus 3. And we're going to have some people side by side, some people don't. It doesn't make any difference. 2x plus y is equal to negative 9. So there's my two expressions. All right. So step one is trying to solve for one of the variables. Out of I got x and y here, I got x, y here. What I'm going to choose is I'm going to try and solve for that y right there because I like using ones that are sort of like all by themselves. I just find that way easier. So if I solve this for y would be equal to negative 9 take away 2x. Okay, so that would be that one solved for y. All right, so now that I've solved for one of the variables, I'm going to substitute that expression into the other one. So I'm going to take this and I'm going to substitute it in right there for that y value. Okay, so I'm going to write out my other expression. Brackets are going to come in handy. Negative 6x plus 7. And in brackets, I've got negative 9 take away 2x is equal to negative 3. Okay, so now we move on to step 3. Got to solve. Okay, well, let's multiply the brackets out. Let's sort of clean things up. So negative 6x, 7 times negative 9 will give me negative 63. And then I've got minus 14x is equal to negative 3. All right, got to combine like terms here. So negative 6x, negative 14x, so I got like negative 20x altogether. Take away 63 is equal to negative 3. All right, so I'm going to add 63 to both sides. So the negative 20x is going to be equal to 60. And then I will divide by negative 20. And I've got x is equal to negative 3. Okay, all right, so I've taken care of that. So now what I can do is I've solved for it. So now I can go back to find the other variable. So now that I know that x is equal to negative 3, I can go back to my other expression and solve for my y value. Now, one of the nicest places to do that would be to use this guy right here, because I have it as y is equal to something. Well, I can use that. I know y is equal to negative 9, and I can substitute my negative 3 in right there. So it'll be negative 9 plus 6, and if I do that, I will have minus 3. So I've got my x value is -3, my y value is also -3, and I can really check this out. Okay, if that's supposed to be -3, that's supposed to be -3. 2 times -3 is -6, plus -3 is -9, so it seems to check out. And if we'd graphed this, that's -3x, -3y, they are coordinate. I mean, that's what these are. So if you actually graph them, these two lines would intersect at -3, -3. Like that's where the intersection would be between those two lines. Okay, all right, let's try another one. All right, let's clean this up, delete that, and get rid of this. Okay, so let's try another one. Okay, let's try this one. We've got -3x plus y is equal to -20. And I've got 4x minus 6y is equal to 22. Okay, let's see what I can do with this one. All right, so I want to solve for one variable. I've got this y all by itself over there, so I'm going to substitute or solve for that. If I solve for y over here, y is going to be equal to -20 plus 3x. That is that rearranged. Then I want to substitute that into my other expression. So I'm going to take this and put it right there. So 4x minus 6, brackets are nice, minus 20 plus 3x equals 22. Okay, let's simplify here. So I've got 4x plus 120, take away 18x is equal to 22. Combine like terms, I've got 4x, take away 18x, it's going to be -14x plus 120 is equal to 22. Subtract 120 from both sides, so -14x. We've got 22, take away 120 would leave me with 98, or sorry, -98. Okay, and then I just have to divide by 14 on both sides, or -14. And that would give me x is equal to 7. So my x value would be 7. So I can then take that and I can substitute that back into one of my original setups. I'm going to take that actually and put it right there, make it a little bit easier. So y would be equal to -20 plus 3 times 7. So -20, 3 times 7 is 21. -20 plus 21 would leave me with 1. And I can check it out. If this is 7 and that's 1, -3 times 7, -21 plus 1, -20, and it checks out. So my answer would be 7, 1. So if I graph the two functions, they would intersect at a coordinate of 7, 1. Okay, so let's try another question. All right, so let's try x plus 8y is equal to -4. And I've got 2x plus 16y is equal to -8. Okay, so solve for the easier one. Well, I got the x by itself over here, so I'm going to solve for that. X is going to be equal to -4 take away 8y, and then I'm going to substitute that in right there. So I've got 2, that's -4 take away 8y, plus 16y is equal to -8. So multiply this out. -8 take away 16y plus 16y is equal to -8. Okay, so -16y plus 16y, well, those guys cancel out. And I've got -8 left because those canceled. -8 is equal to -8. Well, that's kind of strange. Well, it's not actually strange. What happened here is this setup, this one right here, -8, -8, you can add 8 to both sides, you'd have 0 equal to 0. When you have something like this, this would have infinite solutions. Okay, remember we talked about the different types of linear system relationships? This is the type that would be this is a dependent. This is one of the dependent ones. So this dependent relationship. So if we graph these two expressions, these two graphs would have been right on top of each other. Okay, so this is one of the ones where all of the all the coordinates are equal to each other. So everything's going to cancel out. So this is what happens when everything cancels out. If everything disappears, there's infinite solutions. The two lines are right on top of each other. Okay, so this is what happens when you have a dependent system, and they're just basically these two are perfectly equal to each other. Okay, all right, so let's try a different scenario. Okay, so let's try this one. Let's try x plus 3y is equal to 6, and 3x plus 9y is equal to 8. So let's try this one. Okay, well, I've got that x all by itself on the left-hand side, so I'm going to solve for that one. So over here, x would be equal to 6 minus 3y, and then I'm going to substitute this right there. Okay, so this would be 3 bracket 6 minus 3y plus 9y is equal to 8. Okay, so I'm going to multiply with the brackets. So this would be 18, take away 9y, plus 9y is equal to 8. I've got minus 9y and I've got 9y. These guys will actually cancel out to give me 0y. So I've got 18 is equal to 8. Well, that's really strange because there's no way that that is possible. 18 is never going to be equal to 8. Well, when this happens, when you get like an impossible type thing, like absolutely impossible, this is one of those relationships where there is absolutely no solution. So this is what we had before. This is what we called an inconsistent linear relationship. So if you actually graphed it, this is one of those situations where you have the two lines, and if you graph the two lines would be parallel with each other. So these two lines never, ever, ever cross. They're never going to be equal to each other. The other one was close. The previous one we just did, they were always equal to each other. So that was one of the dependent things. That was infinite solutions. This one is totally impossible. So this is a no solution setup. So this is an inconsistent one. So these two lines, if you graphed this line and you graph this line over here, they would be parallel to each other and they would never meet up. Okay, so there's some more practice with substitution. It can get a little labor intensive with, substituting things in. You gotta multiply brackets out, combine like terms, but this is where a lot of the polynomial stuff and combining like terms you work with in grade 9 especially really starts to kick in with your polynomials, combining like terms. And that's always a good idea. Go back, substitute in, see if it actually works out. Writing the answer as a coordinate, that type of stuff also kicks in. Okay, so this is some practice with substitution method for solving linear expressions, and you can easily practice a lot more of the stuff on the worksheet that you guys have.